Okay, the day is actually coming to an end, but before we wrap up, we want to close the day. We are welcoming a representative from Vinaver Medical, Svetlana Krunic, with the talk Application of AI in Medical Imaging. Mr. Svetlana will guide us through the latest AI breakthroughs in medical imaging, from cancer detection to physics-informed models, and how they are transforming diagnostics and personalized medicine. Please, let's all give a warm welcome for Svetlana Krunic.
Hello, everybody. Thank you very much for the invitation. Well, I'm not gonna bore you too much. I'm not gonna go into depth too much. We are gonna keep this light and easy breezy at 6 p.m. So let's start this party. So with healthcare professionals, physicians, nurses, medical staff facing absolutely immense pressure on multiple fronts, could AI be a game changer? That's the question everybody is kind of having in their minds, back of their minds. So actually, I don't think this is the right question. Healthcare professionals and partners like hospitals are not ready to integrate with a certainty that they need at this moment. So we predict that it certainly will be the more of an evolution that leads to the revolution of medical healthcare. And there are many AI and Gen AI models that are rapidly changing this space, and there are probably going to be even more applicable models in the future, but we'll go through some of the most known at this moment through this session. And of course, ML and DNNRs, like the most important at this moment. Like I said, we'll go through some examples, some architecture, some PIN models that are newer to the customer base of ours, and what we do at Vinaver Medical to actually change the healthcare. So, sorry for the gross pictures, but this is our everyday life, so suffer with us a little bit. These are the example that we chose to present to you. Firstly, because of the stories behind them. On your left side, you'll see the mammographic imagery of a 49-year-old woman that had some calcifications. But the interesting thing is, out of 14 physicians that reviewed this imagery, just 7 of them actually predicted the cancer. And what is interesting, with using AI, all 14 physicians decided, oh yeah, this could be a cancer imagery, and that is one of the reasons why we do what we do. And on the right side of mammographic imagery is something that is near and dear to my heart. It is a colonoscopy imagery that determines and helps physicians determine how easy it is to actually extract the polyps that are in the colon. And on your right, you'll see the CT imagery of segmentation of organs. That is very self-explanatory, so I'm not going to go into depth with this. But why is it so important? The patient's comfort is one of the most important things in healthcare, and that may seem very random, But if patients are comfortable during their procedures and if they don't need additional procedures to actually decide for their physician to decide if they need something or medical treatment, further medical treatment, they're happy campers. You know, they're supposed to be comfortable with their physicians, comfortable with their healthcare providers, and there is our opportunity to help hospitals with that. So, precision medicine. This is something that was on the rise for a number of years. If you have the whole spiel about your patient, you have genetic history, patient's history, family history, and you can assess them for risks that are maybe not that obvious. If somebody has a gene that gives the green light to physician that they may possess some cancer cells in some area of their bodies, physician will perform the additional treatments, and this is one of the fastest growing actually healthcare topics right now. It helps streamline workflows and reduces diagnostic errors, because we have what we call a physician's fatigue. This is something that is very real. Physicians are working long hours, nurses are working long hours, and ultimately, with our solutions, it will improve patients' outcomes, prolong their lives, make them more comfortable. And this is something we do, the medical imagery. Why is it important for us to enhance image quality? Even in rapidly evolving and evolved countries, there are hospitals that possess hardware that is of how can I say this, lower quality or older, and it is much easier to buy a software solution you can integrate than actually get a new hardware. Firstly, because hardware is very expensive, and secondary, you actually need to train your physicians, your radiologists, your nursing staff to use it. So it is easier to integrate something that is not gonna disturb their workflow. We'll go through UNets and GANs because they're the most known. And honestly, they're easier to understand, the simple architecture, it won't bore you, and everybody is gonna leave this place hopefully interested in learning more. It will these architectures are usually used to reduce noise in high-resolution imagery, and GANs are actually well known for style transfer. So image segmentation is something that is very essential in computer vision tasks, and it allows not just physicians. Computer vision is a very broad topic, but in our case, divide image into meaningful regions or objects. That can be organs, or that can be objects like calcification on mammographic imagery. Traditional approaches are just not cutting it for our problems. They are limited in terms of efficiency and accuracy, and they just need, you'll need much more data to do what we can do with new architectures. UNet architecture addresses these limitations and gives us more accurate and robust segmentation findings. So you have essentially two parts of this architecture. You have encoder and decoder with output that is quite ordinary segmentation masks. So you have skip connections throughout whole of your architecture, and that's why we call it fully connected convolutional neural network. Skip connections are something that you will maybe struggle with to understand, but I will try to present it in a way that maybe some of you haven't heard about. Firstly, encoder finds the pixels in highly resolutional pictures that, for example, possesses a bike on a picture. And decoders just find a general region where that bike could be. And encoder with their skip connections to decoder will actually tell or concatenate the information about where these pixels are to the outputs of decoder. And I told you about UNet. They're actually introduced as a solution to medical imagery because of the good outputs for our high-resolution pictures. But they found many use cases in, for example, autonomous driving, satellite imagery analysis, and industrial quality control. So GANs, generative adversarial networks. They are consisted of two neural networks, and I like to think about them as siblings. You have generator that generates possible data, and have discriminator, the sibling that always criticizes. The discriminator essentially learns to distinguish the generator's fake data from real data, and that's the whole spiel of GAN architecture. So generator output is connected directly, as you see in the pictures, to the discriminator's input. And the work flow of this architecture is very straightforward. It's in like any neural network ever. Usually we generate or input is a random noise vector, and generator generates output, and then discriminator calculates a possibility value. Then you compare the loss of generator and discriminator, compute the loss of generator and discriminator by comparing the values with desired outputs, and then you update the losses with any architecture with backpropagation. So this is something that is maybe newer. It is physics-informed AI, and it is the part of what we do at Vinaver Medical. So the general idea of this and the general explanation for this and the example that you see at your left side of the slide is a linear harmonic oscillator. You are not dependent on just data, but on physics laws. So you see the neural network with training steps of 500 at the top, and you see that because of the data that is missing, it is not producing the best outcomes. So at the bottom, you see our neural network prediction with a physics-informed model. This is with a bigger training step, but you essentially get the point. With this and information about the physics laws, you'll get much further in your training. So I'll talk about proton therapy. I won't go into details, but essentially to understand what we do at Vinaver Medical, you'll kind of have to know the general opinion and the themes of proton therapy. It is rapidly growing in radiational oncology, and to understand what I'm going to talk about later, I'm going to talk about SPR, or stopping power ratio. It essentially determines how much energy the proton beam will go into the tissue. It is used for cancer treatments and calibration functions. Proton therapy, what is it actually? It uses protons, charged particles, to produce target and destroy tumors while minimizing damages to surrounding healthy tissue. And it is very favorable. It is actually cutting-edge technology in cancer treatment, and especially for children, for organs that are notoriously known for just being difficult to work with, like brain, spinal cord, heart, and eyes. And actually, it is very well known for minimizing the secondary malignancy. And for people with autoimmune diseases, this is one of the key cancer treatments because of the whole other spiel of autoimmune suppressors that are used in diagnostics and actually patients' treatment that are carrying the other secondary problems. Proton therapy is something that is optimized for their treatment too. They're actually more expensive, and particle therapy centers are not widely spread. Actually, there are very high operational costs of them, and therapy in a sense is 10 times higher than the alternatives. The cost of therapy is higher than alternatives. Can AI help? So the problem is, as I said, the high cost, the high operational cost, high treatment cost, and delayed treatment approvals. I'm sorry. And treatment approvals solely depend on CT diagnostic imaging. And actually technology that is used for that is very old. It is something that is well known in the industry, and it is functioning, and it is functioned for a long time. So potential of our solution in Vinaver Medical is that we can do essentially better job at that. So you'll get up to 40% more patients approved, faster insurance approvals, 30% lower bureaucracy and personal costs, and high utilization of your center. So software, as we know it now, use calibration curves because of large, and it is very inconsistent, you'll get, you'll get SPR maps that are integrated into RayStation, which is software that is actually industry standard at this point, and your radiologist is gonna make a treatment for you, but can we do it better? Actually, with our AI-informed physics model, it is possible. Our founder, for his PhD thesis, did a lot of research in this field as a physicist, and he discovered that if you use material maps, because your body consists of water, but if your imagery is done with other subsidies, you can determine much more information, and in combination with SPR, you can get a better treatment plan for your patients. So essentially, if you compare the regular CT software and our software, you'll get up to 10% better NTCP. This essentially means that your healthy tissue that is included into your treatment plan will get less unnecessary radiation, essentially prolonging your life, and actually your comfort as a patient will be larger. Your particle center will have better solutions for your treatments. And I went through a lot of things today. So what is next? In this industry, 5 years is a long time, like 5 centuries in another. So we can't be certain, but maybe diagnostics will improve. We see a lot of new things coming into provision with physics-informed neural networks and many new drug discoveries driven by AI. So maybe new operation rooms of new generation will come out in 5 years, and if I'm here in 5 years, maybe I will talk about that. We can't stress this enough, but I think Vinaver Medical is the part of that future, and we are hoping to be part of it. Yes. Well, with our technology, the cost will probably go down, but as we've seen at the slide up here, if you have more research in the area, more therapy centers that are arising, more competition, the price will certainly go down. But today, well, all we can do is do research and find better solutions, to do better, and actually more insurance companies will see that this is the way to go. Another? Fran, can you wait? You can.
Okay, no, not necessary. I'm totally sold on the proton method because it's less. It causes less side effects, and I happen to have a father-in-law that had some cancer, and it was solved, but he still suffers from the side effects, dry mouth, stuff like that. So anyway, I'm sold on the idea and the science approach to determining the level of impact. I like a lot because it's much more exact than anything I heard. Can you elaborate a little bit on, because I didn't really get it, maybe because I was too enthusiastic about your science approach in general. Where does the AI element really add value to this new technology?
Actually, let me just find the slide. We are generating with AI these material maps. So to find them, well, it's kind of a trade secret, but we are using them to generate them, and it's actually very, you'll get very high noise ratio, and to determine between the masks and how to store them and stuff, you'll use AI for that purposes. Fran?
Would you go on the...
Please.
Just trivia, but it's for the project. It's actually a preponderant question, and that is the name, because you know by now I'm interested in the onomastics and the genesis of names. So how you got the name of the company or the project?
Actually, that's a great question. I never asked Stevan.
Yeah.
I will ask him and I will inform you.
Thanks. And the second question into science, and physics-informed model, and I suppose there are chemistry-informed model and so on and so forth.
I didn't get it. Can you be...
One of your the fundamental ingredients of your project, you have the physics-informed model, right?
Neural network.
Yes, yes. So could you tackle that, and is that, how do I say, well, just let's focus first on physics-informed model.
Well, you have physics laws that are physics laws. You can change them. They're there to exist before us and will exist after us. And that will essentially be the physics-informed part. And neural networks are neural networks. So if you integrate the two, you get physics-informed neural networks.
Naturally, yeah. Obviously. So if they are physics-informed, why are other models are not informed in a similar fashion, and that way we could reduce hallucination?
Well,
because she's brilliant.
That too, I agree. But our problem is, or problems that are physics related in any way, shape or form, are just that. You can't use LLM with physics laws. What physics law do you have in LLM? So this is kind of a rhetorical question that... I'm sorry if I didn't satisfy your curiosity, but...
I have the last question. And then, no, I will. You mentioned a couple of times that Spiel model, and I asked the guys and they don't know what it is. What's that Spiel model?
The Spiel model?
Yeah, you were saying about Spiel model 3 or 4 times. Spiel. What is Spiel?
I have no idea. What do you mean by Spiel, Fred?
Maybe the question can be modified into how we use the word spiel.
Have you used the word Spiel?
No. No, he's making fun of me. Yeah, he told he will, before the presentation, he's...
Very important word.
Spiel?
It's a verb, it's game.
No, but
The Spiel,
no, the spiel when you present it, like I'm going to give you
the
my
whole Spiel,
The whole Spiel, what is the whole Spiel?
the whole story of it, but
for example. Like if I have my lecture.
what is the purpose of this question? You make fun of me, huh?
Yes! Oh my god.
We would love again to thank Ms. Svetlana for this wonderful talk. And before she leaves, we would love to give her a certificate of recognition. Thank you so much for accepting our invitation. Photographers. Thank you so much. All right, what an incredible day it has been here in the Library Hall of DSC MENA 2025. We have witnessed powerful talks really on how AI is reshaping industries, transforming public services, and pushing the boundaries of innovation. From ethical AI to groundbreaking advancements in healthcare, the insights shared today have been nothing short of inspiring. As we wrap up the enriching day, we invite you to continue the celebration and innovation and progress at the closing ceremony in the auditorium. It's time to honor the people, ideas, and the incredible impact we have seen throughout the day. This was Sandy Hussam. We can't see you later. Let's keep the momentum going and look ahead to the future we're shaping together. Thank you.